So today we get to look at lesson 6 on exponents and logs, and we actually get to discover some laws labeled product law, quotient law, and power law. So there's a little bit of investigation to do. I'm going to try to do log 2 base 16 plus log 2 base 8, and then also try to multiply them. I'm going to use my brain power, not my calculator. See if you can do that as well. Uh, So in playing around with my log using the work from 2 lessons ago, where I can just evaluate using my knowledge of base 2, it seems that adding and multiplying have a similar relationship. And if you think about why that is, it comes from the fact that logs actually generate exponents. So the addition of logs is like multiplying powers together, which is why the rule works. So the result is that you can multiply the numbers. So for example, log 2 of 16 times 8 is equal to the same thing as log 2 of 16 plus log 2 of 8. The quotient law, you can guess where that might go. I'll try one of them. Actually, I did both of them. We're working with the same statement, except now we're adding, or we're subtracting instead of adding. So the same substitution applied. And we've got a nice relationship that we're going to be able to record and then get the law. So I kind of like that I don't have to memorize this law. It is on your formula sheet. Hopefully you've been able to secure one. We're under our first and second rule of logs. And you'll notice that the law of changing bases is also there. So we've got the product law and the quotient law. And now we're just going to explore why in the world we'd want to do that. I actually don't know how 12 and 3 are related to 2, but if I can change the format, then it becomes log base 2 of 12 over 3, which is equal to log base 2 of 4, which I know is 2. There's a nice reason for the law. Again, I don't know how 6 is related to 9, 8, or 2, but I'm going to try to apply the law, this time the product law and the quotient law together. So putting the laws together, I get to multiply and divide in the order that they appear. 9 times 8 over 2 certainly makes a number that's more recognizable and relatable to the base of 6. Let's turn the page over. So a nice long one to try class example 2, right, as a single logarithm. Remember, the adding can be understood as timesing. So I've got log base x of 10 times 75 divide by, because of that minus sign, log base x of 2 times 3. So that's log base x of 750 divide by 6. That's how that simplifies into a single logarithm, and I can actually go one step further and divide 750 by 6, which will be 125. So log base x of 125. And then if x is 5, I've got a really nice statement to evaluate. X being 5, so 5 raised to what exponent is equal to 125? Well, we know that that value is 3, and it's probably better if I make that a y. 5 raised to the unknown exponent is 3. So let's move on to that multiple choice question, class example number 4. See if you can apply a similar rule. So this is a long problem trying to reduce these 4 log statements into a single expression. I chose to bracket the end to and move the minus sign outside. It allows me to collect some multiplication terms. So the first two, I get to multiply the arguments of the log together because they're adding. And then the next two, I get to multiply the arguments together, but they're in the denominator. So the result of the top argument multiplied is log base 2 of 2x squared. And then I've got x squared y in the denominator. The x squareds cancel. I've shown that by crossing them off. Then I have log base 2 of 2 over y. And that answer isn't there, so I have to see how that simplifies. Log base 2 of 2 minus log base 2 of y is how that division can be looked at in another way, which I can actually evaluate a part of. 1 minus log base 2 of y. I get a shortcut for the next one, but I just want to show you what that looks like first. So class example number 5 will eventually have a nicer way to solve. I've got 3 log 2p's and 3 log 2q's. Well, what does that mean? It means I have log 2p plus log 2p plus log 2p minus 3 log 2q. But I'm going to simplify that 3 log q. So minus 1 log 2q plus another log 2q plus another log 2q. So these are 3 log p's, base 2, and 3 log 2's. But what's the rule if your p's are being multiplied? That's the product rule. You get to multiply those p's together. What's p times p times p? Oh yeah, p cubed. Log base 2 of p cubed minus log base 2 of q cubed is now what I get to simplify. Minuses turn into division statements. So log base 2 of p cubed over q cubed. And now I get to evaluate it if p over q is 8. See if you can understand what the next rule might become. We're looking to connect how this 3 and this 3 are actually connected to one another. So it seems awkward that this example was early in the class work, but hopefully it'll help us with the law. So I've got log 2p cubed over q cubed, except I knew what p over q was. So I need to move the 3 outside. I was able to do that. So log base 2 of p divided by q raised to the power 3. I get to replace p over q with 8. That's cool. The 3 is still hiding as an exponent. And then the 8 gets to be written as a power of 2. And that's 2 to the exponent 3. Now I have 2 to the 3 raised to the 3, which is 2 to the 9th. And log base 2 of 2 to the 9th is 9. Let's check out that last rule. So we've already seen how 2 log x might become log x squared. 2 log x written in this form becomes log x times x, which is log x squared. And that's going to lead us to the power law. The power law actually allows me to treat this exponent as a coefficient to simplify my work. So it's possible that log x squared can be viewed also as 2 log x. That's the power law. That's what we're going to visit right now. So I'm not supposed to use a calculator. I'm going to use the power law. The 12 can move in front. So I get to write 12 log 4 of 16 But I know what 16 is. That's 12 log 4 of 4 squared. That's equal to 12 times 2, which is 24. And log 10 of the 21, you can probably do that on your calculator, or use the power law, move that 21 down in front, 21 log 10, and the log of 10 is 1 times by 21 is equal to 21. And we've actually seen both of these examples already. Log base 6 of 6 to the n, logs generate exponents, so I simply get my n value. And then when you're taking a look at 6 to the exponent log 6n, how are you getting back a value? I kind of like the last example. If I visualize it in log form, my unknown is in the exponent position, so I'm going to take log base 6 of both sides. So log base 6 of the left-hand side of the equation, 6 to the exponent log n. That generates my exponent, which is log 6 to the n. So log 6 to the n equals log base 6 of 5, or log base 6 of y, which means n must be equal to y, or the value that gets generated. That's it for lesson 6. I hope you have fun with the examples. I hope the sound recorded and I wasn't interrupted, so I'm happy.